So now next, from University of Turin now, we'll talk about mother companion. Mother companion. Okay.
So thanks very much for this opportunity. And, so my aim is to present results trying to explain why force and axioms and actually even large cardinals are bringing maximality properties of the universe of sets. And I will concentrate this series of lectures on a proof of why Woodin's axiom star can be equivalently stated as a model theoretic property of the theory of sets. And this first lecture will actually present the model theoretic background so that we can formulate those results precisely. So let me start with this very basic result, which is the following. We fix tau signature for a first order language. Sorry, let's T, beta tau theory. Tau is a signature, and we let T for all equal C belonging to tau, such that C is universal and T models C. And the following are equivalent. Let T have a bit out. So one T for all is a superset of S for all, and who I always forget the direction. Let me check here. For every M which models T, there exists N superstructure of M such that N is a model of S. Okay, so this theorem is saying that if you start from a model of T, you can enlarge it and make it a model of S. And the request is that is disagreement on the universal fragment. So essentially, there are more universal sentences true here than there are here.
What is this funny symbol between N and M?
The superstructure.
Why is it like square?
Because it's a subset, but it's more than a subset. It is preserving the structure. So
But they are structures.
They are structures.
So, oh, I see. You use that for substructure.
Yes.
Okay.
Yeah.
Yeah.
And the proof. Let me give the proof because it's 2 lines and it's instructive.
Can you have function symbols in that language?
Yes, whatever. I mean, it's a first order signature with function, relation, whatever. So what happens? Well, one direction is easy. So why? Because if you have 2, then it means that whenever you have a model of M, you can enlarge it to a model of T, you enlarge it to a model of S. So you get that every universal sentence which holds in S holds in a superstructure of a model of T, and then it goes down. Okay. So the other direction is the one that is more delicate, and it uses compactness.
This is a question whether it holds for finite.
For finite model. So you are saying that it really needs. I don't think. I think it holds in general. Let me see from the proof if there is some request on the fact that there has been.
No, if you use compactness, I'm sure it's going to it most. But I forget what I said. But it's. Yeah, we can talk about it.
Okay, so you run by contradiction. So if you assume two fails, so let M be such that for no, so N is a model of T, for no N superstructure of M, N which models S, sorry, for N models S. So this is let zero M be the quantified free diagram. And that means that S union delta 0M is inconsistent. Right? Because if it were consistent, the realization of this stuff would be a superstructure of M. Because here, delta 0 diagram says that you can see M inside the structure that realizes this this theory. Okay. Okay. By compactness, there exists there is CA quantifier free, such that S plus CA is inconsistent. Sorry, in here it's a vector, inconsistent for a vector of elements in M. So here I'm confusing a structure with its domain. So there is a tuple and the quantifier free formula, which is realized in the model M, but it cannot be realized in a model S, which is a model of S, which is a superstructure. This is a user compactness. And now the point is that this tuple is all of mu constants. They are not appearing in here because those are the mu constants that one has to define the elementary diagram, not the atomic diagram. Okay, so this means that S deduces the negation of CA, and this means that S deduces the universal quantification over this C. Because these constants are never appearing in S, so we can use the universal rule. And so you find this C that we started with was quantifier free, so the negation is quantifier free. We got a universal sentence which follows from S and cannot hold in this model M. Okay, and M models T plus plus CA, which means that M cannot model this sentence. Okay, so it means that T, so that it means that this sentence, so this sentence belongs to S minus T. Sorry, S for all minus T. So it is a very trivial lemma, but it has a very nice consequence, because now it gives an idea of how to get maximality. Can I erase?
Should we turn the light? Close it. Maybe. Let's try. Yeah, you can also see.
The point is that universal theories are closed under chain. So if you have an increasing chains of models of a universal theory, the union of the chain is a model of the universal theory. So start with M0, which models T, then pick a formula exist X, C, X, A belonging to M0 less than omega. Is this formula consistent with the universal fragment? If so, this is the question, you pass to M1, which models T for all plus exist X, T, X, A, M1, which is the superstructure of M0. And then you use the lemma because now this lemma says that M1 and M0 satisfy both T for all, so you can flip and goes to M2, which now models T, the superstructure of M1, and now you go to and now you go to M3, which is a superstructure of M1 and is making of M2 and is making through some existential sentence, and you continue. And at limit stages, you do not stop because the union of universal sentences is a union of model of a universal theory is a model of that universal theory. And if you continue long enough, at a certain point, at a certain limit stage, you will end up with something that satisfies all existential sentences, all existential formula with parameters occurring in the limit structure that are consistent with the universal fragment. Okay? And this is exactly how in set theory, for example, one proves the consistency of bounded forcing axiom. So we do exactly this type of argument, but we use iteration theorems that say that a certain notion of forcing is preserved through limit stage instead of this fact that a union of chains of universal models are preserved at limits. But if one unfolds the definition, actually you realize that those properties that we are interested in forcings like properness or semi-properness or stationary set preserving are actually properties stating that certain universal properties are preserved. So you are saying there is a certain fragment of universal statements that I want to preserve through my extensions, and this allows me, if I have an iteration theorem that says that at limits I'm not losing these fragments, I can, well, it's not I'm losing this fragment. At limits, I'm preserving the property that implies that those universal statements are fine. So we are making these things harder because we know maybe that at limit the universal theory is fine, but we also need to know that the limit of our forcing construction is still in our forcing construction, because this is how we go to the next stage. Okay.
That's one thing. So here you going from M0 to M1, you fix the formula, or you do it for all?
Well, I have an enumeration of formulas and parameters, and at each stage.
So you do one parameter and one formula
yes,
at one time, and then you want
to
kind of
patch them together. And I mean, I have to run a process which is of length, the size of the structure, to catch up at the limit of that length.
Sorry, one person is why the way you described it, because it's the way you described that those properties that you're preserved, that this kind of forcing preserves in this kind of statements.
Mm-hmm.
So just that really just you can restrict it to preserving some pi1 statements of some symplectic class. But then if this is proved, then essentially by general model theory, it should follow that simply if you take any union of models obtained by forcing from that class, then just the model, like the model theoretic union, should be a model that preserves that class, which doesn't seem to be the case because, you know.
Well, it is a bit delicate. It is a bit delicate because the.
So I mean, where's the catch then? What happens if I
so
take...
what happens is the unique of these properties that is really in the mold of this stuff is stationary set preserving.
Mm-hmm.
That is saying you are preserving being stationary, which is a pi1 sentence, saying you make all curves.
And you have to check that in the union.
And then in the union, if you have an iteration which is nice, the limit is still nice.
Okay.
Okay, can I erase? Let me erase this.
But you know, don't you? Yeah, I'm thinking in terms of analogous a little bit. So you want to have ZFC, so you're not going
Yes,
to take
yes,
a
that's
union
another
model
catch.
ZFC.
Yes. So what happens is in the case of set theory, we will see it is that when you arrive at the limit stage where you have catched your tail, you end up with the theory of H kappa, not with the theory of a model of DFC. But we will see that if you do the things in the proper way, you essentially end with the theory of H kappa, which is an initial segment of a model of DFC. So when you do the next stage, you are not adding new elements in H kappa, you are just putting things on top. So it's really like the way you get from an iteration theorem. The iteration theorem says at limit stage you are getting a model of DFC, but in this process, if you look at what happens about the existential statements, the fragment that you get at the limit stage that is closed under this existential operation is an H kappa.
When you say you get the theory of H kappa, what does it even mean? I mean,
You will
H kappa
see.
is a structure.
Well,
then
H kappa plus. So you will get the theory that says every set has size at most kappa, and it satisfies all axiom of DFC except power set. Okay, so let's now get to the notion of what it means to catch up your tail. So this is the notion of existentially closed model definition given the out theory. And is one, there exists an n superstructure of M such that n is a model of P, and two, M is the sigma one elementary in N if N star if N star model of P. So whenever you pick a superstructure of N that satisfies the theory T, then the sigma one theory reflects down.
That means every existential
Statement with parameters in M, which is true here.
is already,
yes.
So it's kind of saturation.
Yes, so it's bounded force in axiom. Bounded force in axiom are distinct, but in the bounded force in axiom, you say this N is coming from a forcing extension of a certain type. While here you say whatever. There is no.
This EC stand for something?
Existentially closed.
Existentially closed. Okay, and okay, now there is the standard example. Tau equals plus times 1, T equals fields, and M algebraically closed field. Okay, so this is an existentially closed model for the theory of fields, because if you have a polynomial equation with coefficients in the field M, which has the root outside, actually algebraically closed, the roots were already. Okay. And note.
In this condition too, it's a bit strange. Is it so that you assume that M is a submodel of N star, and N star satisfies T?
Yes,
and then
yes, it's not polished. So M contains star and star implied.
yeah. Okay.
Okay, note. C models this, but Q does not. Okay, so what happens? So we start from Q, we go to an algebraic extension which is algebraically closed, and we killed some sigma 1 step sentence. So this is the sigma 1 sentence that you can write in this stuff. The universal sentence was true here. Now it's false in C. You cannot resurrect it. So if you take a superstructure of C, this is going to be false forever. So this is saying, okay, watch out, because in this process, when you start from your model, and you say, okay, I want to saturate my model, you may end up with something that cannot be a substructure of an elementary extension of your model. Okay. And actually, there is a rather delicate analysis of what happens. I don't know if it's worth going back, but maybe yes. Say that. So, and on the other hand, note that exists x plus x equals 0. Okay, is of a different type. You can add it to the theory of fields, and if you add it, you are adding much more information. You are saying your field is of characteristic 2. So you add just one single sentence, and you are actually, so you add this existential statement to your theory, and you are fixing the characteristic, and actually you are saying also a universal sentence. So in the theory of fields, this is so fields plus let's call this E, fields plus sorry, let's call this E. Field plus exist x px imply for all x. Okay, so what is, so you see you have two existential sentences, but they are of a very different nature, because this one you add to the theory of fields and you are not changing the universal theory. This one you are adding to the theory of fields and you are changing the universal theory. Here you have a richer universal theory, but you obtained it adding an existential sentence. So say that C is conservative for universal fragment of T. If T for all plus C for all is equal to T for all. Sorry, and yeah, maybe this is the weakest notion. I mean, you could also put, maybe it's better like. Okay, so you're adding a sentence such that if you look at the universal consequences, you have not changed it. And you see, this is the conservative over the theory of fields, universally conservative over the theory of fields. This is not. Okay. And key fact, which I won't prove, but it's not particularly hard. Let T be our theory, and M be T is essentially closed. Then M models C for all pi to sentences T such that T is universally conservative over. Okay, so what happens is that, well, if you have that this C is universally conservative over T, it means that essentially by a bit of tweaking you can make this T true in I mean you take off the universal quantifier, you consider the psi where you substitute the free variable with the parameters here, you can make it true in some bigger model of M because it is universally conservative. That's the key fact. And then you can reflect back. Okay. And so we can now come to the key model theoretic notion, which is saying how you get maximality for first order theory of, I mean, this type of existentially closed model. So what is the problem of this notion of being existentially closed? Is that you have a very nice semantic notion. So given a theory T, you can define the class of existentially closed model for T. But then, is it an elementary class? Do you have a theory S that describes this class, or you're ending up with something that is not isolated by a first order theory? And that's where you have the notion of model companionship.
But sorry, but this is very sensitive to the signature.
Yes, yes.
This is
yes,
a bit of
yes,
a problem.
Yes. Yes, it is. Definition. Let TS be town theories. T is the model companion of S. Actually, it's better to use the other way. It's more consistent with my previous notation. T is axiomatized. Well, T is axiomatized. Well, actually, this is a consequence. Let's say the models of T equal M such that, models of S. S is the model companion of T. Models of S are M such that M is the T existential. Okay.
So it is the theory of the T essentially closed model.
Yes. And well, the theorem assume S is the model companion of T. Then S is axiomatized by C such that C is pi 2 and S is and C is universally conservative over okay, so how do you axiomatize this family of existentially closed models for T? Well, you take the pi 2 sentences and you check whether to make when you find a model of T for all and the pi 2 sentence, you are making true some other. I mean, if well, the point is actually apologies. Here it's important. You have to check that T for all plus C for all is equal to T for all. These are the C that you are putting in. If it is a pi 2 sentence, you check that if you take the universal consequences of T and you get the pi 2 sentence, the universal consequences of this theory are exactly the same. You have not added one, a new one.
Does it make a difference? It seems it does, by what you say. If instead of T universal, you just have T.
Yes,
T prime.
typically it happens that T plus psi is inconsistent. For example, psi can be the pi2 sentence that says every set has size at most aleph one, at most countable. And then
Oh, I see.
it
That's
is
your-
okay.
So here, you're never going to take T and S together, like the S is contradicts T.
In general,
in general,
I mean,
right.
yes.
But it's consistent
yes.
with the.
So,
with
for
the-
example, so
the
this can be
universal.
illuminating. So, for example, ACF is a model companion of fields. Well, in this case, you see that the theory of fields is a sub-theory of ACF, and also in rings with not zero divisors. So those are not fields. Pardon, rings with not zero divisors, which are not fields. This is also first order axiomatizable. And any model of these theories, any model of this theory is not a model of is not an algebraically closed field. But when you perform this process, you start from a model of this theory, you add an existential solution to a polynomial that, and then you put a model of this theory, and you continue this way at limit stages. When you end up and you close off, you will end up with an algebraically closed field. Okay. So the question is, what happens if you perform this process with set theory? And the delicate point is that it really depends, the universal theory really depends on the signature in which you axiomatize that theory. Because you change the signature, you make the signature more expressive, more sentences become universal, and what you get by the closure process can be very, very different.
So in principle, you can turn every theory into a universal
Yes,
theory by
yes.
using scaling functions.
Yes, yes. And then, yes, this is absolutely uninformative.
So it's all about the signature.
Yes. Okay, and let me. So you see that one very fine point. So suppose we put ourselves in the context where T is a complete theory, or just that T is complete for universal sentence. So it decides every universal sentence whether it is true or false. And then what happens? You get that conservative for T for all means just that psi is consistent with the universal, with the T for all. So psi, you can find a model of T for all and psi. So it is saying that the model companion is axiomatized by the pi2 sentence, which are consistent. Okay. And for those who know star, well, star has an equivalent formulation that says star holds if and only if for any pi2 sentence with predicates for the non-stationary ideal and for universal reverse sets, if the pi2 sentence holds in some forcing extension, then it actually falls in the star model. Okay, so it's exactly like this, but the difference is that here is pi2 holding in whatever model, not obtained by forcing. Okay, but otherwise it's exactly the same.
But they should be the same.
Yes, and actually they are the same. So this is the theorem that I'm going to present in this tutorial.
But isn't that also consequence of the fact that star decides the full theory of H2? So if something was, say, pi 2, which is somehow consistent but not by forcing, or then
Well, it decides that full theory with respect to forcing. You have to decide. I mean, in principle, there could be some pi2 sentence that you're able to make true with the universal fragment of set theory by some method which is not forcing, and then those pi2 sentence may, in principle, they may not hold in the models of stuff. So that's
you're
the,
saying this doesn't happen. Forcing is
this
the
doesn't
only.
happen. Yes. So this is saying forcing is the only mean to get consistency of certain statements, provided you choose the right language. I mean, because we have to be very careful in this choice of statement. Okay. And maybe there is still something that I want to say. So yes, model completeness. So and let me say theorem. Well, the first definition. T is model complete with well, definition theorem, let's say, and it's called the Robinson test. If any of the following holds. Allora, one, he is the model companion or if you want T for all, it's the same. Two, for all M substructure of N model of T, M is sigma 1 elementary in N or even fully elementary in N. Okay, so you can choose whichever of the three
Models, so they are both models of the
Yes, yeah.
plural is with an S at the end.
Models. So essentially you cannot the substructure relation corresponds to the elementary substructure relation corresponds to the sigma 1 elementary relation. 3 for every tau formula for every quantifier 3 tau formula Pxy. So this is actually the way one proves the model completeness. That's why it's called model. There exists tau quantifier 3 theta x z such that T proves for all x exists y pitch x y is equivalent to for all z theta. So what is this condition saying? Every concept is delta 1. So because then you can for well actually for every, so here for S3, but with C any formula. So C is any formula, but tau remains quantifier free. So it is saying essentially every formula is equivalent to a universal formula. Okay, but you see, this is giving a pi2 axiomatization of the theory. So actually, you can check that exactly these formulas. So the formula given here are giving the axiomatization of the theory, and these formulas are saying all the concepts in the theory are delta one. So they are upward absolute because you take the sigma one presentation, and
you've said with psi being quantifier free, does that also make theta quantifier? Sorry, being
Yes.
any formula, does that?
and then C X Y any, but theta quantifier free.
And when you say quantifier free, you don't even allow bounded quantifier.
No quantifier. I mean, there is no notion of bounded quantifier, so that's the point.
Yes, except when you get to set theory.
Yes, but I will eliminate this boring actually this disturbing bounded quantifiers.
But boring?
No, boring, no, but they are disturbing because essentially they will not fit into this picture,
Okay,
and they need a separate treatment that really brings you, I mean, to lose all the control that you have between these semantic notions and the syntactic characterization. So you see, this is how you prove model completeness. So you take a quantifier-free formula, you take an existential formula, and you have to show that it is equivalent to a universal formula. If you can do that, you have shown a model completeness. And then you see, then it is saying the model completion is realizing all the pi2 sentences that are consistent with the theory. Well, how much time do I have?
The question is, when did you?
I think 10:40.
Yeah, it was like 20 minutes.
Anyways. Okay, and now let me come to set theory. Okay, so the point is that all this machinery is very nice, but it's really very much sensitive to the signature. And in set theory, we never paid so much attention to this matter. So for example, we say P is sigma, well, it's delta 0. Well, but when you, in P epsilon formula, but when you really write it down without using the bounded quantifier, P could have arbitrary high complexity. So for example, you can check that X equals Y, Z, written by formalizing Kuratowski pair. Is sigma 2. Okay. So this is very bad. I mean, this is the most trivial concept. And to express this concept, you already have to get to sigma 2 formula in the sigma 2 in epsilon. Okay, so if you just take the signature epsilon, this concept is sigma 2. X contained in Y is pi 1. It says for all Z, X belongs to Z, Z belongs to X, implies Z belongs to Y. Okay, so this is a simple concept and it's universal. Okay, so this, but we are used to say, for example, P is sigma 1 in parameter A. Okay, and we have a very clear meaning of what this means. It doesn't mean it is sigma 1 as an epsilon formula. It means it is sigma 1 in an extended signature that we never take care of spelling out in detail. And this extended signature essentially allows for using all delta 1 concepts as atomic predicates. Okay, so let's take this.
Delta one or delta zero?
Well, actually, you take the delta zero, but often it is convenient that you can also allow some provably delta one concepts as predicates in your statement. Because, for example, the Mostovsky collapse is a delta one concept, but usually you want to use it as a let's say function symbol or whatever in the concept you are stating. Okay. So let's take this and give what I think is the natural signature we use in set theory. Is this fine?
So why don't you just declare delta zero formula?
Yes.
To be
Yes.
just,
Yes. That's what one does. But epsilon delta zero is equal to RT such that T is delta zero union F C, well, let's say GI less than 10 union I don't know what's the name of the rudimentary function in the standard terminology. Okay. So what you want to allow yourself to have a function symbol for all the standard set theoretic operations. Okay, but finite list. It's better that it is a finite list because you see the problem with function symbol. You have to have in your theory that the theory proves for all x there exists just a y pxy, and this is a pi2 sentence. So.
So what are these? Is it a Gödel operations or what?
Yes, yes. So, for example, as in that. Okay, so you are free to use all this type of operation. I think they suffice. And eventually, if need be, you also add some delta one concept, like the. Actually, you can show that whenever you have a delta one concept, you can freely add to your signature, and you're not changing the universal consequences. Okay, so you can add it freely, and it's no problem. You can add it as a predicate, and you can add it as a function symbol, provided your theory proves that that delta one concept is a graph of function. So this is basic. Well, and maybe you also add the constant for empty set and for bound. Okay. So this is epsilon delta zero. And we are essentially, this is the standard natural signature in which we formalize that theory. Okay, and now we are looking for the existentially closed models for this theory. And we note the following. For all x, there exists an f from omega to x surjective. So there exists an f from omega surjective is phi 2 for epsilon delta 0 and false in h omega 1 epsilon delta 0, and this is sigma 1 in v epsilon delta 0. Okay, so this is saying so what does that mean? It means that if you take the universal fragment of set theory in this signature, whatever model of set theory you take, the pi2 sentence saying every set is countable is consistent with that universal fragment. So it means that this pi2 sentence is going to fall into the model companion. If it ever exists, this pi2 sentence is going to fall inside. So this is saying if there is a model companion for this theory, that will include this sentence. Okay. And similarly, you can check that, for example, the replacement axiom for delta 1 form properties also is formulated by a pi2 property. So it means that in the model companion theory, the replacement axiom for pi2 for delta 1 properties will be true in the existentially closed model. And well, extensionality is universal, so it will be true. And what are the other axioms? Well, I mean, you can check, and essentially everything is non-problematic. The unique problematic axiom, even choice is not problematic. So problematic is pi2. It says for every x, well, essentially choice is here. This is choice. Okay, if you change so if I put x to omega injective, then I have clearly the formulation. So the unique problematic axiom is power set. Power set, if you write down power set in this signature, it is a pi3 statement. So it does not reflect down, and actually it fails here, for example, because it's too complicated. Okay, and let me just prove also this one lemma. Let kappa be infinite, then h kappa plus epsilon delta 0 a in kappa n is sigma 1 elementary b epsilon delta 0 a. Okay, so this is an extended version of Levy absoluteness. Levy absoluteness is this, where you don't allow predicates for the subsets of omega. Okay. Sorry, apologies, not kappa. Sorry, a subset of power set of kappa. So in the case of H-1, I'm taking subsets of the reals, power set of omega. So these are, I'm adding predicates for subset of the reals, and this is an extended version of Levy absoluteness, where you allow not only just the delta 0 formula, but you're allowing also to talk about subset of the reals. And here it is very important that we don't use bounded quantification, because if you say something for all x belonging to a p x, well, this is not, I mean, this can in principle be, this is not a bounded quantification, okay? Because you unfold it and it's universal. Okay? And also a very careful statement, okay? So it's clear from the very definition of this stuff that these, those are interpreted by predicate symbols. So those are not meant as objects. They cannot be, because they are subset of the power set of kappa. Okay, so these are predicates.
So you add all.
You can add all, yes. Okay. So what is this? What is this lemma saying? It is saying, okay, you can even expand this signature, adding predicates for the subset of the powers. So you fix a cardinal kappa, and say you want to study the maximal theory of set theory when you can talk about this cardinal kappa. So for example, here we were fixing the case of kappa equals omega. Okay, but now suppose that we want to study kappa omega 1. Okay, and then this is saying, well, the universal model will satisfy the statement for all x, x size less than, there is a surjection of kappa onto x. So you will end up with a theory of H kappa plus. Yes.
Is there a distinction between, you've written a subset of P capital N, N in omega. Is there a distinction between that and just P capital less than omega? In this
Well, the point is you have to fix the arity, because now you are really working in first order language. So every predicate symbol has a fixed arity.
So are we including every possible predicate here or just one particular way?
All possible. I mean, you can choose. You can choose a finitely many, and then, I mean, if you can prove for finitely many, you have to prove all.
So you might as well choose just one. It's the
Yes.
same. Really.
Yes, it's the same. Okay, and maybe I prove this because it's also easy and instructive. So essentially, you do the same proof of Levi absoluteness, but you keep track of the fact that there is a proof that V models exist x P x A or A belong. Well, we can take off the subscript because H kappa plus is closed under finite subsequence for A belonging to H kappa plus. P M substructure of V theta. Well, and suppose that theta is large enough so that this statement reflects to V theta, such that kappa is contained in M, and what else we need that M has type kappa, and I guess that's all. Let N be the transitive collapse. Sorry, and A belongs to M such that so this is an unfortunate choice, such that PBA also. Then we get that N models P of pi B A. A is not moved because kappa is a subset of M, and A is an element of H kappa plus, so its transitive closure has size at most kappa, and when you collapse down a structure that contains kappa, it's the first ordinal moved is going to be kappa plus, and the size. Okay. And now we just have to check that that the predicates, those predicates are correctly mapped down to N. So we just have to check what is A intersection N. Assume A belongs to M, and A is a subset of the power set of kappa. And what is phi of A? Well, phi of A by definition is phi of A intersection M. And since A, what are the elements in A? The elements in A are subset of kappa, so they are not moved by the transitive collapse. So this is equal to A intersection M. Okay, and so if you take N epsilon delta 0, epsilon delta 0, and then just A intersection M, this is going to be a substructure of H kappa plus epsilon delta 0, epsilon delta 0 A, as witnessed by the anti-collapsing map, because it is the identity, well, sorry, by taking the identity. So what is the map? This is carefully. So this is going here, and the identity on N. Okay. This is okay because you see here I'm taking what happens here. I just have subset of kappa, and if I have take the identity of on N, there's no problem. They're moved correctly. And I know that this predicate is correctly mapped here. Okay, but then here I have that N models P of phi B A, and I suppose that this was the predicate subset of power set of kappa that appeared here, and I moved using this substructure relation, and I get that H kappa plus models of phi B. So what was the key point? The key point was that I chose a subset of H kappa plus, whose elements have always bounded rank. So I cannot increase in rank in the elements of the subset. So if I took a subset of H kappa plus like kappa plus, this breaks down, because when I collapse down, I will have the interpretation of the stuff is going too much high. But when I take elements of bounded rank, then there's no problem. Okay, how much time is left?
Time is up.
Okay, then
But he is participant, sorry.
I think it's fine to stop
Is it
here.
good place to stop?
Yeah.
Okay, so we'll continue.
So where are you heading?
Well, I want to prove that if you take here the right type of predicates, which will be the universal reverse sets and the non-stationary ideal, here you put HLF2, and you get that the theory of this